Welcome back to Computer Lessons.
For thousands of years, humans looked at the stars to navigate the oceans. Today, we have replaced the stars with artificial moons made of silicon and gold. We have surrounded our planet with a digital shell that allows us to communicate instantly and pinpoint our location to within a few centimeters. This is the final frontier of the internet: space. To understand satellite internet, we must first understand gravity and orbits. For decades, traditional communication satellites were parked in what is known as geostationary orbit, or GEO. This is a specific ring about 35,000 kilometers above the equator, where the satellite moves at the exact same speed as the Earth's rotation. From the ground, a GEO satellite appears perfectly still in the sky. This is convenient because you can point a satellite dish at it once and never move it again. However, the physics of this distance creates a massive problem for the internet: latency. Even at the speed of light, the signal takes about 240 milliseconds to travel up to the satellite and back down to Earth. When you add the return trip for the server's response, you get a half-second delay. This makes real-time activities like video calls or online gaming impossible. The lag is simply dictated by the laws of physics. Enter the new era of low Earth orbit, or LEO. Companies like SpaceX with Starlink and others with OneWeb are launching satellites into an orbit only 550 kilometers high. This is 60 times closer than the old GEO satellites, reducing the signal travel time to a tiny fraction. Because they are so close to Earth, LEO satellites must travel incredibly fast to avoid falling out of the sky. They orbit the planet every 90 minutes, screaming across the sky at 27,000 kilometers per hour. This creates a complex engineering challenge. Your stationary home dish must track a moving target. Your Starlink dish is actually a phased array antenna. It contains hundreds of tiny antennas that use electronic beamforming to steer the radio beam instantly without physically moving the dish. It hands off your connection from one satellite to the next every few minutes, seamlessly maintaining the link. The most advanced feature of these new constellations is the inter-satellite laser link. Satellites shoot lasers at each other in the vacuum of space to create a mesh network. Crucially, light travels about 47% faster in a vacuum than it does in glass fiber. This means that for long distances, like London to New York, a laser link in space can theoretically be faster than a fiber optic cable under the ocean. We are building a backbone in the sky that bypasses the terrestrial infrastructure entirely. But communication is only half the story. The other half is navigation. The Global Positioning System, or GPS, is perhaps the most critical utility in the modern world. It is owned by the US government, but is free for everyone to use. It works on a principle called Trilateration, which is often confused with triangulation, but they are different. Triangulation measures angles, trilateration measures distance. A GPS satellite simply broadcasts two things: its current position and the exact time the signal was sent. Your phone receives this signal and notes the time of arrival. By subtracting the send time from the arrival time, your phone calculates how long the signal took to travel. Since radio waves travel at the speed of light, it can calculate exactly how far away the satellite is. Imagine a sphere around the satellite with a radius equal to that distance. You are somewhere on the surface of that sphere. If you measure the distance to a second satellite, you get a second sphere. The intersection of two spheres is a circle. A third satellite gives you a third sphere, which intersects the circle at just 2 points. One point is in space and the other is on Earth. That is your location. To make this work, the timing must be unbelievably precise. An error of just 1 microsecond, 1/1,000,000th of a second, would result in a position error of 300 meters. This is why every GPS satellite carries multiple atomic clocks, using cesium or rubidium atoms to keep perfect time. However, the engineering of GPS revealed a shocking truth about our universe. Albert Einstein was right. According to the theory of special relativity, because the satellites are moving fast, 14,000 kilometers per hour, time slows down for them by about 7 microseconds per day compared to clocks on Earth. But according to general relativity, because the satellites are far away from Earth's heavy gravity well, time speeds up for them by about 45 microseconds per day. Combining these two opposing effects, time on a GPS satellite runs exactly 38 microseconds faster every day than time on your phone. If engineers did not program the satellite clocks to tick slightly slower to compensate for this relativistic effect, GPS would drift by about 10 kilometers every single day. Your navigation system is literally a daily proof that time is relative, and gravity bends space-time. GPS signals are incredibly weak. By the time they reach Earth, they are like a light bulb seen from 20,000 kilometers away. This is why GPS fails indoors or in tunnels. To help, your phone uses AGPS, or Assisted GPS. It downloads a map of where the satellites are supposed to be over the cellular network, drastically speeding up the time to first fix. Without this internet assistance, a standalone GPS receiver can take up to 12 minutes to download the full almanac from the satellites themselves. The US isn't the only player anymore. Russia has GLONASS, the European Union has Galileo, and China has Beidou. Modern receiver chips in your smartphone listen to all of these constellations simultaneously to increase accuracy and reliability. However, all this activity has created a dangerous situation: space debris. There are millions of pieces of dead satellites, rocket stages, and paint flecks orbiting Earth like bullets. A collision at orbital speeds releases more debris, increasing the chance of further collisions. This creates a runaway chain reaction scenario known as the Kessler Syndrome. If this happens, a belt of debris could form around the Earth, destroying our satellites and trapping us on the planet for centuries, unable to launch rockets safely. Space sustainability is now a critical engineering discipline. To prevent this, modern satellites are designed to deorbit themselves at the end of their life. They use their last remaining fuel to dive into the atmosphere and burn up. Starlink satellites are designed to be demisable, meaning they completely vaporize upon re-entry with zero debris hitting the ground. We are also looking beyond Earth. As we send humans to Mars, we cannot use standard internet protocols like TCP/IP because the light speed delay is between 4 and 24 minutes. We are developing DTN, or Delay Tolerant Networking. In DTN, there is no end-to-end connection. Data is stored at each node, a satellite or relay station, until the next link becomes available. It is a store and forward architecture designed for the vast distances of the solar system. We have now covered the entire connectivity stack, from the copper in your walls to the fiber under the ocean, the towers in your city, and the lasers in space. We know how the data moves. But where does the data actually live? When you save a file to the cloud, it doesn't float in the sky. It lives in a fortress of concrete, cooling systems, and spinning disks. We are leaving the transport layer and entering the destination. In the next video, we will open the heavy doors of the data center. We will explore cloud computing, virtualization, and the massive physical infrastructure that holds the world's knowledge.
Tell me in the comments, do you rely blindly on GPS to get everywhere, or could you still navigate using paper maps and road signs if the satellites went dark? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching, and keep learning.